Welcome. In this video we're going to look at the work done by a non-constant force on an object, and we're going to throw in some calculus at the end so that we can deal with non-geometrical shapes in our force versus position graphs. So here we've got a mass sitting on a frictionless surface for the time being, and let's say that we're going to apply some force. And this is a non-constant force. It's going to depend not on the time, but it's going to depend on the position. And we are going to move this block by a certain displacement, delta r. And now we've already talked about the fact that the work done is simply equal to the force times that displacement, if the force and the displacement are in the same direction. And let's take a look at what a graph of F versus r would look like here. If our force is constant, then we would have a nice horizontal line. So it doesn't depend on the position, it's constant. And so if we do F times R, what we can see is that we will get the area of that rectangle, because the height of the rectangle is that force F, and the width of that rectangle is that delta R. And we should understand at this point that if we're looking at the area under a curve, then we're looking at the integral. So it looks like the work done by a force is equal to the integral of F times R. So rewriting our equation here then, the work done by a non-constant force would equal the integral of that force, and it's going to depend on R, and we are going to integrate that over some infinitely small chunk of R dr. And we'd be integrating with our limits from the initial R value, the initial position, to the final position. So graphically then we see that the work is interpreted as the area underneath a force versus position graph, and then mathematically the work is the integral of force with respect to position. So let's take a look first graphically at how this would work. So let's look at a force versus position graph. And this force versus position graph is a nice linear function. So the force is increasing as R increases. So if we want to find the work done from some initial R to some final R, then we see that we have the area of a nice little trapezoid here. All right, and so you could use the trapezoid area equation if you would like, or you could find the area of that triangle right there and add in the area of that rectangle right there. And so graphically, if we have a nice geometric shape, then we can simply find the area of that shape, and we interpret that as the work done. We can see that this area is above the R axis, and so above the axis means positive work. If we had a graph like this that went some F to R there, and we want to find the area, the work done from R initial to R final here, then we see that part of that is going to be positive work and part of that is going to be negative work. Above the axis would be positive, below the axis would be negative. Negative. And we can interpret this graphically saying, oh, well, there's more positive area than there is negative area, so the overall work done here is positive. And we cannot forget the relationship between work and kinetic energy. Work is equal to the change in kinetic energy. So a positive area, positive work, means that we have an increase in kinetic energy. So we could say that kinetic energy here goes up. And overall here we have positive work, which means also that the kinetic energy would increase. In both of these cases, we're going to see the object speeding up. Now, those are nice graphical geometric shapes that we can simply use area formulas to find, but what if we don't have a nice geometric shape for our force function? So here we have a nice little force function. This is for an object moving only in the x direction, only horizontally. And so we have a force function with respect to position of x squared minus 4x plus 7. That's going to be a lovely little parabola, and it might look something like that. So let's say we want to know the work done from x equals 1 meter to x equals 4 meters. And so let's see here on the graph, we're looking at the work done from here at x equals 1 to the work done over here, x equals 4 meters. And it is the area underneath that parabola, but we can't use a nice little geometric formula to calculate that, so we need to go to the integral. So then the work done is going to be the integral of the force function, x squared minus 4x plus 7. And we're going to be integrating that with respect to the position. And we're going to integrate it from the lower limit to the upper limit, x initial to x final. So we use the power rule here. We get the work done is equal to 1/3 x cubed minus 2x squared plus 7x. And we are going to be evaluating that from 1 to 4. And so plugging in our limits of integration, we have 1/3 times 4 cubed minus 2 times 4 squared plus 7 times 4. And we're going to have to subtract. Oh, let's get rid of that and do it a little bit nicer. Minus that function evaluated at 1, which is going to be 1/3 minus 2 plus 7. I'm going to go ahead and go to the calculator. And surprisingly enough, that works out to the nice, neat number of 12, provided I punched everything into my calculator correctly. And the unit for work always is joules. So we interpret the area under this curve as 12 joules worth of work. It is positive 12 joules worth of work, so this object would be increasing in kinetic energy, also increasing in speed. And we could use this to find speed, provided we knew the mass and the initial velocity, and we could look at this as the change in kinetic energy, which would be k final minus k initial. And again, the importance of work is not calculating the work itself. The importance of work is looking at its relationship to the change in energy of an object. Here, that force is adding energy to the object, adding kinetic energy, speeding it up. Lastly here, I wanted to draw a distinction between integrating a force function with respect to position and integrating a force function with respect to time. And we've already done the one on the right-hand side, integrating with respect to time, but we looked at it through the lens of the fact that force is mass times the acceleration. So if we have our acceleration function with respect to time, then we can simply integrate that acceleration function with respect to time. And we get some information about the change in the velocity of the object. Remember that the area underneath that acceleration graph would give you the change in the velocity. So that's different from what we're doing here. Here we don't have the force as a function of time, we have the force as a function of position. And we're going to see one very important force that changes with respect to position is a spring force. So when we do the integral of this, we also get some information about the change in velocity, because the work done is equal to that integral of f of x with respect to x, but that's equal to also, remember, the change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. So this is another powerful tool in our toolbox. If we have a force function with respect to time, then over here we're going to integrate it and look at it through the lens of Newton's second law. On this side, if we have the force that changes with respect to position, we can integrate that and get the change in kinetic energy. In both cases, whether we have the force as a function of time or the force as a function now of position, we can get that change in velocity. And that's a very important consequence. We're going to be looking at this again through an even different lens when we get to start talking about momentum and changes in momentum. That's it for now. See you next time.